So now let's derive the Eulerian form of mass conservation for a continuum. So the Eulerian form of conservation of mass is the form that's typically used for fluid flows and is often referred to as the continuity equation. So stating mass conservation in words from the point of view of a fixed Eulerian spatial observer watching fluid flow into and out of a fixed spatial region, which is often referred to in fluid mechanics as a control volume, we can write the following. The rate of change of mass contained in the fixed spatial region R must equal the rate at which mass flows into that region R across its boundary S. So mathematically, the rate of change of mass would be the integral of the rate of change of density with respect to volume. So the triple integral over R of d rho dt d little v. And then the rate at which mass flows into the region, if we subtract that from both sides, we would now add the rate at which mass flows out of the region, and that's given by the surface integral of rho times v dot n ds, where v is the velocity vector, n is the outward normal to s. So v dot n represents the component of the velocity that is going out away from, across the surface away from R. And that velocity is convecting mass with it of density rho. So multiplying rho times that component of the velocity gives the rate of change at which mass is leaving R, which is the negative of the rate at which mass is entering R, and hence it's on the other side. So now, applying the divergence theorem to convert this surface integral into a volume integral, we obtain that the triple integral over R of d rho dt plus the divergence of rho v with respect to volume is equal to 0. And again, since our region R is entirely arbitrary, that means the integrand itself, the terms inside the integral, must be identically satisfied. This term must be identically 0. And so we get del rho del t plus div rho v is equal to 0. And this is our first version of the Eulerian form of conservation of mass. Now writing this in index notation, this would be del rho del t plus vi del rho del xi plus rho del vi del xi, because this divergence of a product will result in two terms when we expand the derivative. Notice these first two terms, del rho del t plus vi del rho del xi, are the same as the material derivative capital D rho dt. And the second term, del vi del xi, is just the divergence of v times rho. So this is the second form of the conservation of mass for an Eulerian description. Now, again, if we have an incompressible material, then the density from the point of view of the material is constant. In other words, the material derivative of the density d rho dt is equal to 0. And therefore, our conservation of mass simplifies to div v, which is del vi del xi, which is also dii, the trace of the rate of deformation tensor, must all be 0. So that is the Eulerian form of conservation of mass for an incompressible continuum. So next time we'll go on and we'll derive the conservation laws for linear momentum, angular momentum, and energy. Let's do an exercise making use of the Eulerian form of mass conservation. If a flow field has a density distribution given by rho equals k times x2, and velocity components given by v equals 2x1, 1, and 0, and whereabouts in the flow field is the flow at steady state? Is it A at x1 equals minus k, B at x2 equals k upon 2, C at x1 plus x2 equals k, D at x2 equals minus 1/2, or E at x1 equals minus 1/2? So to solve this, we make use of the continuity equation, for which we'll need the divergence of the velocity, which is just 2. So that's del 2x1 with respect to x1 plus 0, and the gradient of rho, which will be 0, k, 0. Now, the continuity equation is del rho del t plus the divergence of rho times v is equal to 0. And expanding that, we get del rho del t plus rho times div v plus v dot grad p is equal to 0, which then gives us that del rho del t plus k times x2 times 2, divergence of v, plus 1 times k is equal to 0. Now the problem is at steady state when del rho del t is equal to 0, which will mean that 2 times kx2 plus k is equal to 0, which gives us that 2x2 is equal to minus 1, or x2 equals minus 1/2, which was choice D.